In this lesson, we're going to learn about partitions and their use in the Linux operating system. Now, aside from managing user access to your Linux systems, one of the most foundational tasks is the management of data storage. There are many different ways to divide, format, or otherwise organize the data that's going to be stored on your systems, and Linux gives you many different tools for doing this. Using these tools, you'll ultimately make it easier for authorized users to work with data. Now, there are many different types of storage devices that are supported by the Linux operating system. Common types include hard disk drives that use magnetic storage technology to store your data, solid-state drives that use non-mechanical solid-state technology to store your data, USB thumb drives that use flash memory technology to store your data, and external storage drives that use several different types of technologies and usually connect to the computer through a peripheral interface rather than being internally connected. Now, in Linux, devices are referred to as either block or character devices. Block devices are things like storage devices. These are things like hard drives, solid-state drives, and USB drives. And all of these can be read from or written to in blocks of data. Character devices, on the other hand, are devices like keyboards, mice, serial ports, and other things like that that can read from or write to streams of data one character at a time. Now, a file system is a data structure that's going to be used by an operating system to store, retrieve, organize, and manage files and directories on a given storage device. It also maintains information about the data, such as the date of creation and the modification of individual files, the size of the files on that storage device, the type of files, and the permissions associated with those files. But the operating system does not interpret the data contained in the files itself, because this task is handled by specific applications. Now, the file systems vary depending on several different things, such as the purpose of the file systems, the information they store about the individual files, and the way they store data, as well as the data security mechanisms that are going to be implemented. Linux systems support several different types of systems, including FAT, ext2, ext3, ext4, XFS, and BTRFS. These file systems can be used for varying situations depending on your specific user needs. FAT, or the File Allocation Table, is an older file system that is compatible with many different operating systems, including all versions of Unix, Windows, and Mac OS X. It does not provide the same capabilities as more modern file systems, and is typically going to be used when you need to maintain compatibility between all these different operating systems. ext2, on the other hand, is a native Linux file system, and it's used in some older releases, and it's still supported in your current Linux releases. ext3 is a more modern version of a native Linux file system. ext3 is much faster in recovering data, and it does a better job of ensuring data integrity in the case of abrupt system shutdowns than ext2 did. Another default file system in Linux distributions is ext4, and this supports really large volumes, up to 1 exabyte of data, and also supports file sizes of up to 16 terabytes in one file. XFS is a 64-bit high-performance journaling file system that provides fast recovery and can handle really large files efficiently as well. The last type of file system we have is known as BTRFS. BTRFS is a modern copy-on-write file system for Linux that's designed with advanced features in order to provide fault tolerance, repair, and easy administration of your file system. BTRFS supports volumes of up to 16 exabytes in size, files of up to 16 exabytes in size, and it supports a maximum of 18 quintillion files on each volume. Now, some file systems function as network protocols as well, and this enables the sharing of data over a network. For example, the SMB protocol, also known as Server Message Block, is going to allow users to share access to files and other resources over a local area network, which is known as a LAN. SMB clients make requests for resources to SMB servers, and these servers will respond and provide the appropriate level of access. Now, in addition to SMB, we also have something known as CIFS. Now, CIFS is the Common Internet File System, and it's a specific implementation of SMB that is rarely in use today. Instead, Microsoft designed it as a successor to SMB version 1, but SMB version 2 and 3 have long since replaced version 1 and CIFS. However, some Linux distributions will still use the name CIFS in some of the tools when they're referring to tools that support SMB, so it is something you need to be aware of. Now, another protocol you need to be aware of is NFS. NFS stands for the Network File System. The network file system offers similar functionality to SMB, but NFS and SMB are not compatible with each other. If you're going to be using all Linux clients and servers in an environment, then you'll probably want to use NFS because it actually has some better features than SMB. But if you're going to use a mixture of Windows and Linux systems, you want to rely on SMB because SMB is the default inside of Windows and is supported right out the bat, where NFS is not supported by Windows by default. Now, another thing we need to talk about is something known as an index node. This is also abbreviated as an inode. Now, an index node is an object that stores metadata about a file or directory on a given file system. This metadata can include time-based values like when the file was created and last modified. It can have permission and ownership information. It can have the block locations of the file's data on a storage device and other pieces of miscellaneous information. In instances where there is an unexpected interruption, the file system can actually quickly recover itself through journaling because it records changes to those files that have not been made to the file system yet inside of this inode. Now, the journaling process involves describing all the changes that must be made to the drive, the background processing, performing pending changes when rebooting, and discarding incomplete entries. Another type of file system you need to be aware of is known as a virtual file system, or VFS. Now, a virtual file system is going to be created as a common software interface that sits between the kernel and the real file system. In effect, the VFS is going to translate a real file system's details over to the kernel. That way, the file system appears to be identical to any other file system. With VFS, you can mount many different types of file systems on the same Linux installation, and they're all going to appear uniform to the user and all the applications on that system. File system labels are going to be assigned to those file systems for easy identification by VFS. These labels may be up to 16 characters long, and they can be displayed or changed using the E2 label command for ext-based file systems and the xfs_admin command for xfs-based file systems. Now, the first task in managing storage is to partition a storage device and format the partition with one of these file systems. This will make the section of the device available for reading and writing of the data once you've formatted it. Now, when I use the term partition, this simply means it's a section of the storage drive that is logically acting as a separate drive. It enables you to convert a large drive into smaller, more manageable chunks, leading to a better organization of your data. Now, there are three types of partitions you can use, and each one has specific features. We have primary partitions, extended partitions, and logical partitions. Primary partitions contain one file system or logical drive, and it's sometimes referred to as a volume. The swap file system and the boot partition are normally created in the primary partition. Linux likes to push some of its unused files from RAM to the swap space to free up actual physical memory. This goes to what we call the swap space. This swap space is simply a partition on the storage device that's going to be used when the system runs out of physical RAM or physical memory. An extended partition can contain several file systems as well. These are referred to as logical drives. This partition type does not contain any data, and it has a separate partition table. The logical partition is a part of the physical drive that's been partitioned off and allocated as an independent unit and functions as a separate drive. There's also going to be times when you need to create a new partition table or modify existing entries on the partition table. To do this, you're going to use the fdisk utility. This is a text-based, menu-driven program that's used to create, modify, or delete partitions on a given storage drive. Fdisk will also enable you to specify the size of those partitions. Now, the fdisk utility supports a number of command line options, including things like Option-B. If you use Option-B and then the sector size, you're going to be able to specify the number of drive sectors. If you use Option-H, heads, this will be used to specify the number of drive heads. If you use Option-S, sectors, this is going to be used to specify the number of sectors per track. If you use Option-S with a lowercase s and then the partition, this will be used to print out the partition size in blocks. The Option-L is going to be used to list all the partition tables for a given device. Now, aside from supplying different command line options, you can also choose various options when you're working in the fdisk menu itself, including the options of N, D, P, W, and Q. Option N is going to be used to create new partitions. Option D is going to be used to delete or remove a partition. Option P is used to list out the existing partitions, almost like a print-to-screen function. Option W is going to be used to write the changes to the drive and exit the utility. Option Q is going to be used to cancel the changes made and exit the utility as well. Now, in addition to fdisk, there's another utility we can use to manage our partitions. This is known as the GNU parted command. The GNU parted command is going to be particularly useful when you're creating partitions on new storage drives. This tool can be used to create, destroy, and resize partitions. The parted command runs the GNU parted utility, and just like fdisk, parted includes a menu-driven interactive mode where you can input various options. The option select is going to be used to choose which device or partition you want to modify. The option mkpart is going to be used to create a partition or make a partition with a specific file system type. Option print is going to be used to list out the partition table to the screen. Option resize part is going to be used to resize or modify the end position of a given partition. Option rm is going to be used to delete a partition, and option quit is going to be used to exit the GNU parted utility. After you create a partition, you can't add a file system to that partition unless the kernel can read it from the partition table. So instead of rebooting the system, it's better to run the command partprobe after you run fdisk or the parted command. If you do this, it makes the kernel aware of your new partition configurations that you just made. The partprobe command is going to be used to update the kernel with the changes that now exist within the given partition table. The command first checks the partition table, and if there's any changes, it automatically updates the kernel with those changes. Another important command to know is the make file system command, which is written as mkfs. The mkfs command is used to build a Linux file system on a device, which is normally going to be a drive partition. Now, we're going to talk about some of the options of the mkfs command here and give you some of their basic descriptions. If you want to learn more, you can always type man mkfs at your command prompt and learn more about it. First, we have option -v. This is used to produce verbose output, where the output message is going to keep updating constantly as the program is processing. If instead you use option -V, this will produce verbose output as well, but it'll also include all the file system specific commands that are being executed. If you use option -t and the file system type, you're going to be specifying the type of file system you want built on this computer. If you use option fs-options, it's going to be used to pass the file system specific options to the file system builder. If you use option -c, it's going to be used to check the device for any bad blocks before it builds the file system. If you use option -l and the file name, it's going to actually read the list of bad blocks from a specified file that you've already run this command against. So when it comes down to the make file system command, there's really two ways to run it. The first is to type mkfs, set up your options, and then enter your device name. The second way is to use mkfs, putting your file system type, your options, and the device name. Another thing we need to cover is the fstab file. Now, the fstab file is a configuration file that stores information about storage devices and partitions, and where and how those partitions should be mounted. The fstab file is going to be located in the /etc directory. It's going to be read by the system during the boot up process, and it can be edited only by your root user. The fstab file consists of a number of lines, one for each file system that the system knows about. Each line has 6 fields that are going to be separated by spaces or tabs. The first field is the device or partition name, and it specifies the name of the device or file system that you want to mount. The default mount point indicates where the file system is going to be mounted, so it might be / for the root file system as an example. The file system type will also specify the type of file system used by that device or partition. The mount options field specifies a set of comma-separated options that will be activated when the file system is mounted. The dump options field indicates if the dump utility should back up the file system. The fsck options field will specify the order in which the fsck utility or the file system checker utility should check the file system. Another file we need to talk about is located in the /etc directory, and it's known as crypttab or crypttab. The /etc/crypttab file performs a similar function to the fstab file, but its purpose is to store information about encrypted devices and partitions that have to be unlocked and mounted on system boot. Its format is going to be similar to the fstab file, but it includes an optional password field for unlocking encrypted devices. Now, as we've talked about all these different utilities, the overall process of setting up storage devices for use on Linux machines includes just a few key things you need to do. First, you need to partition the storage device using a tool like fdisk or parted. Then, you need to format the partition using a file system, and this will be done using something like mkfs or the make file system tool. Then, you need to add the formatted partition to the fs tab file so it can be configured by the system to run at boot up. In Linux, everything is going to be treated as a file, even a directory or an entire disk's volume or partition. When you look at a file system, you're going to see it written out as a directory known as /dev for device. Now, a /dev directory is a special file that contains details about all the files and subdirectories that are housed within it. Linux uses naming conventions so that storage devices are easily located by the system whenever they're attached and when the system boots up. For storage devices, the naming convention is typically expressed in 3 parts. Let's take a look at an example. If I have a device called /dev/sda1, this actually tells me a lot about this device. The first part of that, the SD portion, refers to the specific type of controller that that device is using. The second portion, the A, is going to refer to the first whole drive because A is the first letter of the alphabet. Then, if we had a second drive, it would be B. If we had a third drive, it would be C, and so on. Now, the third part of this is the number 1, and the number 1 refers to the first partition on this drive. If we had 2 partitions or 3 partitions, we would have a 2 or a 3 here. So, when I have something like /dev/sda1, we know we have the first storage device and the first partition on that storage device because it is SDA1. In addition to using this naming convention, Linux also has several different persistent naming schemes to help us identify devices. Controller-based naming can sometimes be problematic in systems with more than one type of the same controller. So, instead, we can use a persistent naming scheme to overcome this and make it more predictable. If I'm using a persistent naming scheme that's based on the device's hardware serial number, I'm going to do this by using /dev/disk/ID number. If I'm using a persistent naming scheme that refers to an identifier based on the shortest physical path to the device, I might use something like /dev/disk/path. Finally, if I'm going to use a persistent naming scheme based on the universally unique identifier, or UUID, I would write this as /dev/disk/UUID, and this would refer to that universally unique identifier that's assigned to the device when the file system was first created on it. The last thing we need to discuss is some special character devices that exist under the /dev directory. This includes the /dev/null, /dev/0, and /dev/urandom. As I mentioned earlier in this lesson, everything in Linux is treated as a file and mounted on the file system. Just like we can mount a hard drive to the /dev/sda1 directory in the file system in order to interact with it, we can also use things like /dev/null and /dev/0 and /dev/urandom, which are special character devices that are installed by default in most Linux distributions, and each of these are used for a specific purpose. The /dev/null special character device is a special type of virtual device that allows you to discard anything that you send to it or redirect into it. Think of the /dev/null as a big black hole, and any data streams or character streams that you don't want to deal with or save to a file, you can simply redirect those into the /dev/null and it's going to disappear forever. If you try to read from the /dev/null device, you're simply going to receive an end of file message because you've effectively reached the end of that file because that file is always empty and contains nothing. The /dev/0 special character device is going to be used as a special type of virtual device that will return a null character anytime you read from it. If you redirect the output to the /dev/0 device, it is going to discard the data just like the /dev/null device did. But the big difference is, when you try to read from /dev/0, it's going to act differently than /dev/null did. You're not going to get that end of file back immediately, but instead, it's going to send you back the ASCII null character of the hexadecimal value of 0x00. Now, why might you use /dev/0 if all it does is send you back an endless stream of zeros whenever you read from it? Well, this is actually useful when you're trying to sanitize a hard drive by overwriting it with a bunch of zeros. To do this, you can simply use the dd command, which stands for disk duplicator. you enter dd space if equals /dev/0 space of equals /dev/sda1 space bs equals 1 GB space count equals 1024. And this command will overwrite a 1 terabyte hard disk that is mounted as SDA1 with a series of zeros across the entire drive for the entire 1 terabyte in size using block sizes of 1 gigabyte each. Now the next special character device we need to discuss is the /dev/urandom. /dev/urandom is a special type of virtual device that will return a randomized series of pseudo-random numbers. For example, if you're creating a program or script on a Linux system and you want to generate random numbers for something, like determining which side of a rolled dice would be returned by your program, you can use /dev/urandom to do that. For example, let's say I wanted to get 5 random characters. I can enter head-c 5/dev/urandom and then hit enter. This will return 5 random characters from that special character device called /dev/urandom. As you can see, there are multiple different ways for us to reference block and character devices on a Linux system, depending on what your use case is.